A family wants to create a fenced pen for their pet rabbits. The pen is to be built against their house with three sides of fence, one, two, three, and the house forming a rectangular pen. If they have 24 meters of fencing, what's the maximum area they can fence off? So you get this wall for free because the house is there anyway, and you have 24 meters with which to make these three walls. So we're trying to max out the area, which would be length times width, so that's no problem. The trouble is this has two variables in it, and we hate those. Yes, we could do that product rule thing that I demonstrated in one of the older examples, but we avoid that whenever we can. If we could get this down to one variable, that would be really nice. So we need to find some other way of relating the length and the width that we can use to maybe replace one of them. And there is something. There's the fact that these three sides have to add up to 24 meters, which means two widths and a length make a grand total of 24. If you take the w's to the other side, you get L equals 24 minus 2W. Now, there's no particular reason why I used the L here. You could solve this for W instead, although I did notice that if I do it this way, I won't end up with a fraction. And if you solve this for W, you're going to get 12 minus 1 half L, which is a little less nice to work with. So you have a choice of which variable you isolate here, and make it easy on yourself whenever you can. So in our area formula, anywhere that there's an L, we can write 24 minus 2W instead. So let's do that and see what we get. A equals L times W. So our area is minus 2W squared plus 24W. I switched the order of these terms to get decreasing order because I'm a little bit obsessive about that. So that's the area of our rabbit pen, and if we want to maximize it, the idea is, if this is your house, you could make a pen like this that has a massive length and hardly any width, and it would have very little area. Or you could make a pen like this, which has crazy width and almost no length, again, very little area. So if you're doing width to area, too little width, you don't get much area. Too much width, again, you don't get much area. But in between, there should be a spot where we maximize the area, and that's the spot where dAdW, the derivative, equals 0. So if you take one thing away from this section, it should be that maxima or minima or optimal values happen when the derivative equals 0. If you don't know what to do with a question like this, take the derivative, set it to 0, solve it. That will almost always be part of the way to the solution. If we do that here, we get dAdW equals 2 times minus 2 is minus 4W plus 24. Where does that equal 0? Well, we'd need minus 4W to equal minus 24, which would mean W should be 6. So these two sides, we know what they are now. They should be 6 meters. That's also 6 meters. And if we have a total of 24 meters of fencing, here we've used 12 of it. That leaves 12 for the length. So the maximum area to be fenced off is a 6 by 12 rectangle. Oh, and they say what is the maximum area they can fence off? That would be 6 times 12, so the best area we can give the bunnies is 72 square meters. So this is the best area, and this, 6 by 12, is how you get it.